Hello, everyone. Thank you all for being here. My name's Ben. I'm an iOS engineer at Autodesk, and today I'm speaking with Alec, who's an Android engineer at Square. Today, we're going to talk about our experiences shipping Kotlin multiplatform in our mobile apps, and hopefully some things that you'll be able to take away from those experiences. But first, we're going to get started by talking a bit about the apps where we ship multiplatform. So again, I'm Ben. I work at Autodesk, and I work on a construction app called PlanGrid. It's a construction app that construction workers use on construction sites, so construction. And if you're a PlanGrid user, you use the app to keep track of your blueprint sheets, issues, basically any workflow that you would more traditionally do on paper. More modern job sites will use the PlanGrid app to do that. And so I have a screenshot here from the app. And we're looking at a blueprint sheet from the LA Natural History Museum. And so there's a couple different things going on here. So first, in the PlanGrid app, you can make edits to your project, like this markup. And when you make these edits, they're synced to other users' devices on your project. Also, in the PlanGrid app, when we find references to references to sheets in your project, we'll automatically turn those into links so that you can follow them and navigate through your project. So hopefully, this gives you a sense of PlanGrid as a construction collaboration tool.
Sweet, yeah, and then I work on CashApp. CashApp's a financial services app, so it's for primarily P2P payments. Like, this is the main screen of the app, and you can see you can send and request money from people. But we do a lot of other financial services beyond that, like you can make card payments or cash in and out of a bank account. And really, the app is driven by those transactions, so they sort of show up as individual rows in your history, and that's that tab for this to the right there. But that's primarily the important thing to get out of this is that we're storing a lot of payments and transactions offline that are kept on the phone. Some other interesting stuff that we're doing is some types of live info. In this case, we're showing a Bitcoin graph, so it's the live price of Bitcoin over time. And then we also perform some smoothing over this. There's smoothing on this graph. We also do card signatures that we smooth. And so there's some heavy math algorithmic operations that we do that are typically done both on iOS and on Android. So that's a little bit of context on that. Between the two of us, it's kind of interesting. We come from different backgrounds, which we're hoping will give a little bit more perspective to this talk. So Ben comes primarily from an iOS background, and I come primarily from an Android background. His app is with construction, mine is with financial services. And we have similar team sizes, but you'll see the kind of problems we're actually solving are very similar.
All right, so for this talk, there are a couple things I think you should know about the PlanGrid app. So first is that it's designed to work well offline. It turns out construction sites don't come out of the box with internet. And so as a PlanGrid user, you typically go into a trailer that exists on your job site throughout the day to sync up the edits that you've made in your PlanGrid project. And so to facilitate that, we have a sync system that we maintain on multiple platforms. In fact, we maintain it on iOS, Android, and Windows. And so we got into multi-platform so that we could solve this and consolidate all of that into a single shared library.
And then on the cache side, the big thing to get out of this is we have this ability to search through all of the transactions that you've made. And because we have all of those transactions client side, we wanted it to be a really quick user experience. So we also perform that search client side. And both the Android and iOS apps are backed by this SQLite database. And so all of the queries and business logic that sits above that to do the search is the same among the two of them. In addition to that, there's a lot of business logic. When I think about those smoothing algorithms, those are things that we were sitting down with iOS engineers working on together. And so even though we were doing the same code, we were sort of writing it twice. And that was another way that we saw this multi-platform coming in. So yeah, even though we have very similar things, we're doing the same sort of stuff. We're deploying to both Android and iOS. And it's really this shared business layer. You'll hear this a lot with multi-platform. This is really where Kotlin multi-platform succeeds. And we're both starting with that idea of there's an offline first store of things that we want to be able to access, models that sit on top of that, and then business logic that goes a layer above it. And so this is really where multi-platform fits in super nicely. Once you get above this layer, you're starting to get into those more platform-specific things. I want to talk a little bit more about the tool chain as well, because it doesn't just support Android and iOS. It also supports things like deploying to the web, to Windows. And so what multi-platform really is, Kotlin multi-platform, it's the tool chain that enables doing all of this. So it's a Gradle plugin where you write a single source set, and then you're able to compile it to any of these platforms, like to the web, Android, iOS, or Windows. One thing we often see is like a little bit of confusion between what Kotlin multi-platform is and then what Kotlin native is. The key distinction here is that Kotlin native is an actual compiler backend that's being used to compile to things like iOS or Windows, where you have to compile to the architecture. Right? Like on Android, you have a JVM, so you're able to compile code that runs on the JVM, and that'll run on multiple devices. But there's no VM in something like an iPhone, so you have to compile to the actual CPU architecture. You could technically use Kotlin native to compile to Android's architecture or to compile to WebAssembly, for example, but chances are you're probably just going to be using like JVM or Kotlin 2.js. So yeah, there's different compiler backends that Kotlin multi-platform actually uses, and Kotlin native is one of those things.
All right, so today, Alec and I are going to talk through what we think are the 3 stages to shipping a new multi-platform project on an existing team. So first, we're going to talk about how to educate your team, bring them up to speed on Kotlin multi-platform, as well as how you get to deciding on Kotlin multi-platform for your cross-platform solution. Then we're going to talk about actually building out your shared library and some practical advice for doing that. Finally, once you've built out your shared library, you're going to want to ship it. So we're going to talk about some things you should look out for when you're ready to finally ship, as well as some practical advice for turning it into something you're comfortably iterating on long term. All right, so jumping right in, we'll start talking about educating your team. All right, so at this point, you're deciding on Kotlin multi-platform, and that means you've decided for your team you want cross-platform to be a part of your development process. Well, I think it's important to understand that bringing cross-platform onto your team means taking on a pretty significant initial setup cost. Your team's going to need to learn new tools that your cross-platform shared code base uses to integrate with the rest of your platforms. Your team's also going to need to learn a new language if they want to contribute to that shared code base. And finally, when you go to integrate your code base into each of your platforms, some, when you integrate it, might go exactly as you pictured. But then when you go to integrate it on other platforms, it might require a bit more hand-holding, maybe an extra Gradle task here or code generation to make it feel nicer to your downstream native code. But the idea is that once you get over this initial hump, there is all of this expected value you hope to gain out of your shared code base on the other side. So this idea that there's this initial setup cost isn't necessarily a bad thing. It's just going to force you to really focus on what is that expected value that I hope to get out of this multi-platform effort. And so at PlanGrid, we had this problem of diverging sync systems. At some point, we wrote this, and on day 1, it worked exactly the same way on each platform. But over time, sync system on each platform acquired its own bugs. Some even became more capable than others, leaving other platforms behind. And so that's why we got involved in multi-platform, to create the shared code base and consolidate all of that.
Yeah, on the cache side, it was an existing shared code base. So one thing I didn't mention about search is that before Kotlin multi-platform was a thing, we had actually started sharing all of that search logic through JavaScript. So there was essentially a JS runtime on both Android and iOS, and JavaScript would get shipped to each client by the server and then get executed at runtime to run those queries. It's a really horrible setup. I don't really recommend it. And so when Kotlin multi-platform became a thing, there was this very enticing, shtick for the iOS team, which is, hey, we can take this JS runtime that you don't like and replace it with something native. It'll still be shared code. It'll still be the same SQLite. And so it was very easy to convince the iOS team that this was something that would be worthwhile. And then it's still something that, because we have the JS engine that already exists for it, it's also something that we could A/B test, for example. Depending on the flag that you have, we could use either the JS engine or the Kotlin native engine. And since we were early into Kotlin native, it was very important that we exercised it and realized if it was something we could invest more into. So this does force you to ask some very serious questions, too, that I think will become very important as you invest over time in Kotlin native. By figuring out the actual thing that you want to solve, you're also going to get an understanding of the tools that you need to understand to solve it. So things like Gradle, or in our case, like the JS engine. Understanding those tools is going to become super important because those are the things you're also going to need to educate the rest of your team about. But I think maybe the most important thing is identifying what that common goal is, the thing that everyone is rallying around, that everyone wants to do. Because with multi-platform, it can get really hard to figure out which things should I be putting in multi-platform. We'll talk a little bit more about that later. But the idea is that you have this thesis almost that you can always go back to, where if you're unsure about have we accomplished the multi-platform thing, you can think back to that common goal that everyone had. So those were some of the reasons that Ben and I had where we were going to our teams and making a good case for Kotlin multi-platform. But there's a lot of other ones, too, that you can kind of cite. I think for Android especially, Node.js and it being in Kotlin means that it's nothing really new for the Android team, so it shouldn't be too hard to convince that. But even for iOS, there's things like Objective-C interop that'll make it feel a little bit more native, which is really nice. And then what we really want to highlight is like the community and JetBrains here. This is a huge reason why we think Kotlin multi-platform is going to be a huge success. Because JetBrains has this huge focus on tooling, it's something that you don't really need to worry about where you might with other cross-platform solutions. And just the community in general, there's a lot of like momentum going behind it, and it's all very transparent. So it's easy to see sort of like what things are going to be coming up. And if you run into issues, you're going to get like really quick responses on it. But one thing you might notice is like we have Objective-C interop on here, but the iOS community is actually moving towards Swift. So what's going on there?
Yeah, so as an iOS developer, like myself, you probably spent the last couple of years, if you're on a new code base, building it from the ground up in Swift, or if you're on a legacy code base, slowly marching away from Objective-C towards an all-Swift code base. So, you might be a little concerned when Kotlin Native comes onto your team and you're looking through Objective-C interop at those APIs. And so I think the answer to this question, this common question that we see, it comes in two parts. The first is that the Objective-C header that you do get from Kotlin Native is actually very well annotated from Swift. And what that means is that when Swift goes and translates that header when you're writing code, the APIs feel very Swifty, for lack of a better word. And so much so that I've even had coworkers that have started working with our shared library and were surprised to find an Objective-C header when I went and pointed them to answer a question. The other important point, I think, to recognize is that this is actually the status quo for the vast majority of Apple's system frameworks. Most of their frameworks are still an Objective-C header. They're nicely annotated so that they feel Swifty when you're interacting with them. Now, Apple is moving sort of towards more and more native Swift-only frameworks with Swift UI and Combine. And hopefully JetBrains will adapt as well. So the next thing that's natural to ask about when you're looking at adopting a new language is, what are the performance, what are the expectations you can have out of performance of writing in this language? Well, the good news is in Kotlin, if you're coming from the JVM world, there are really no changes in your expectations there, because when building Kotlin multi-platform for Android or JVM, you can lean on all the expectations you had out of the JVM before. But on the iOS side, it's a bit of a different story, right? Because you're going to use the Kotlin native backend to build your library for iOS. So it's really important that you profile any performance-sensitive code that you have in your app and file issues. And over time, those issues have resulted in real performance gains to the Kotlin native tooling each release. And another thing to point out here, too, is that Kotlin Native actually has really great interop with C, which is a little bit harder to do on the JVM side. And so if you do have really performance-sensitive code, you can always drop into C if need be, which we have done in PlanGrid once or twice. All right, so Alec, what about value types?
Yeah, so with value types, there's sort of two angles that I look at it from. If you're thinking about value types in the way that they work in like C, where it's a memory thing, that they're staying on the stack and you never have to have heap allocations, then there's nothing that really does that right now for Kotlin Native, but there's also nothing that does that for the JVM, so there's no real reason for Kotlin to go and implement that now. If we do, like if Project Valhalla becomes a thing and we get proper value types in the JVM, then I could see Kotlin catching up to that, and like maybe it ends up happening in native. But at least from like the memory side, that's something that's you can't really do right now. The other argument I'll hear sometimes is that, especially with Swift, like Swift struct types are copy on write, and what that means is whenever you go to change one of the fields, it actually creates a new copy of it. And so those copy semantics are really great because it enforces immutability, and that you can get in Kotlin. Like we have data classes for that in the copy method, and those will translate well to Kotlin Native. So if the thing you're worried about is actually like immutability and these really nice value types essentially, then data classes will get that. Speaking of memory, you might see stuff around a garbage collector if you look around the documentation, which is a little bit confusing and also scary if you've worked with other cross-platform things. So what's going on there? There isn't a garbage collector. It uses reference counting the same way that something like Swift or Objective-C does. So it's able to automatically deallocate things. But there is a cycle collector, which is worth knowing about. What I mean by that is like even with reference counting, it's possible to have things leak if there's a cycle in the memory references. In Swift, you would handle this by having like weak reference annotations so that it can clean that up once one of the things is deallocated. But those annotations don't exist in Kotlin Native. And so instead, there's a cycle collector that will run periodically within Kotlin Native code. The important thing to know about it is it's not like a stop the world cycle collector. That's the thing that I think scares most people off. It's not something that's going to like halt the main thread. As long as you're running your Kotlin native on a background thread, only that thread is going to stop to do the cycle collection. And it's really fast as well. So it's not actually something that you really need to be concerned about as long as you are operating off of the main thread there. If you want more information specifically on the cycle collector, it's called Bacon's algorithm. You can look this up, Bacon's algorithm for cycle collection. It's like a concurrent algorithm for cycle collection. You can get more information on it there. Also, I'm going entirely off of comments that I've seen in the Kotlin native code base, so I'm assuming those are all accurate. If they're not, then everything I've said is a lie, but I'm pretty sure that that's still up to date. What about libraries, and what can we use there for Kotlin native?
Yeah, so when you're getting into a new programming language, it's natural to ask about the library ecosystem you can expect to use there. So again, if you're coming at this as someone from the JVM or Android world, you're often sort of saddened to find out that those JVM distributions of libraries you're used to being able to use are not going to work in multi-platform because you're going to be building for non-JVM architectures like the ones that Kotlin Native supports. So you're going to have to look for those multi-platform, special multi-platform distributions of libraries. These are libraries that use the multi-platform plugin and distribute one artifact port per target that they support. Now, the sort of kicker here is that because the Kotlin Native ABI is unstable, and some of those artifacts are built with Kotlin Native and have binary in them, that means that every Kotlin Native major upgrade, like from 1.340 to 1.350, is going to require that you wait on publishers to republish their binaries so that you can then pull them into your multi-platform library. Now, obviously, a lot of this changed this morning with the announcements of portable klibs, so stay tuned for that. The next thing I want to address, and sort of the final thing for this education topic, is this idea of common code. Because when my teammates first start writing their first multi-platform code, this is something that after they've been writing for a while, realize they don't completely understand how common code works. So I want to quickly go over how that works. And I personally like to look at it from the perspective of your multi-platform library's outputs. So let's say we're making a multi-platform library for iOS and Android. It's reasonable to expect that you might get outputs like this: a framework for iOS and an Android archive for Android. Now, to get these outputs, you're going to need sources, and those go in source sets. So you'll have your common code, which goes in your common main. That's the code that is going to be shared between all of your outputs. And then you have your platform-specific source sets, your iOS main and Android main for iOS and Android, respectively. And so what happens is when you go to build for each of these outputs, it's going to build common main with your platform-specific source set. So if I go to build for iOS, it's going to build my common main code with my iOS main code and bundle that together to produce my iOS framework. Similarly, for Android, it'll build your common main along with your Android main together to produce your Android archive. And it's also useful to look at this in terms of how it works when you actually need something platform-specific, too, since that can also be a source of confusion. So let's say we need a lock primitive that we want to be able to use from our common code. We use the expect keywords for that. So we might make an expect class called lock. And so now common main knows that there's going to be a lock class that will come from one of these platform-specific source sets at compile time. And so then when we go to build our iOS framework, it'll just build in the actual implementation from our iOS main, and that'll be the implementation that our common main gets to use in our iOS framework. Same deal for Android. When we go and build for Android, the actual implementation is what common main gets to use in the Android archive. And so that's just a quick overview of how common code works if it's your first time trying to understand how this works. All right, so that's it for education, and we're going to move right along into actually building out your shared library. So I've been talking about things in terms of these source sets, and when we're thinking about actually building out our shared library, it's important to think critically about the platform-specific code that you add to your library over time. Because we really want to avoid a situation where we end up with a library like this, where basically we end up with really big iOS and Android main source sets and really small common main. Now we're basically back to where we were before multi-platform, and we're maintaining two platform-specific code bases, right? Ideally, we keep things so that most of our functionality is written in common main so that it's written and maintained once, and we only go out to our iOS main and Android main when we absolutely need to for our platform specifics. And this is really useful for us at PlanGrid, too, because when we got started on this project, we knew we were going to support iOS and Android out of the gate, and Windows was going to come in later. And so when they came in, it was really easy for them to implement the very few actual implementations that we needed them to in the code base for them to start building a library that was workable for them. And it turns out that building a library and maintaining this configuration of a big common main and small small platform-specific source sets is trickier than we expected. And so Alec is going to talk about some examples of what I mean by that.
Yeah, so the way that we typically will go through this is a pretty simple flowchart in terms of what code you're dealing with and where it should land within the different source sets. So the first thing you need to actually ask yourself is the thing platform agnostic? If the answer is yes, this is like the simplest case. You just put it in common main. There's no platform dependencies, so it should be able to live there pretty easily. If it's not, then you need to ask yourself a second question, which is if other common code is going to use this. And if the answer to this is yes, then this is where you have to use those like expect types that actually get actualized in the platform code. And then finally, if it's not something that's going to get used in common code, that's when you just like go out to the platform. And you really have two options there. You could have it in that platform-specific source set within the Kotlin multi-platform module, or you could just have it live in like the host application, which is something we'll talk a little bit more about later. So to illustrate this, we're actually going to go through search as we implemented it on cache and see how it fits in with this flowchart. And the important thing you need to know about search is there's essentially three main functionalities that it's doing. The first one is creating that SQLite database. So it's actually a separate SQLite DB than the one that's storing all of your transactions, and it's only for filtering. So you need to create this actual database that's going to store, it has like a FTS table for SQLite that it's able to use to actually do those text searches. The second thing it does is it'll perform inserts and updates onto that database, and then the final thing is queries. But I'm going to start back with the actual creation of the database and ask this first question of that. So when we're creating a database, is that something that's going to be platform agnostic? The answer to this one is no, because every time you go to create a SQLite database on Android, you use the Android like support SQLite framework to do it. And on iOS, we're using a library called SQLiter, which works for Kotlin native. So we have platform-specific implementations of SQLite that we have to use. But when we ask if other common code is going to use it, well, the database in our case is supposed to be lazy, something that gets created actually when you go to query instead of doing it at like runtime init. So in that case, it is getting called by the Kotlin common code because the Kotlin common code is the thing that's going to be performing that query. So yes, it does, and so we need to put it into common main, and this is where we're going to use that expect class. So this is what it looks like for us. We're essentially expecting this factory that knows how to create a SQLite driver, and so when we're in the query code that's inside of common, we can ask the driver, we can ask the database factory to create a driver, and then if it's on iOS, it'll use the native one, and then on Android, it'll use support SQLite. And so that's how we're able to actually create the DB from common code. So we'll ask the same question now for the seeding stuff, so when we're inserting, updating, and deleting from the database. That stuff is also not platform agnostic, and the reason for that is that the types that it's actually inserting into the database are coming from platform-specific types. So like, for example, on Android, we use a library called Wire to generate data classes based off of protobufs. But those data classes aren't multi-platform. There's something that's specific to Android, and those are the things that we want to insert into this table. So because those things aren't actually platform agnostic, we can't do like the insertion inside of common code. And so because we can't do it inside of common code, that's when we would go back out to the actual platform-specific one and use it from there. What that actually ends up looking like, one of the nice things about the multi-platform plugin is you can actually have dependencies out from your multi-platform module back into the main like host application. So in this case, if we're in the same repository as the Protos module, we can just depend on it and then create this new API. So this doesn't live in common main. This lives in like the Android lib main, but it's able to reference types that are only on Android. So in this case, it's that sync entity type, because that's what we're inserting into our search table. On the iOS side, well, on Android, we were able to do this, and it was all in Kotlin, so it still felt very native. But if we wanted to do the same thing, we would have to use C-interop in order to interop back with the things that were in Swiftland. And it's a lot of extra work in order to like create those APIs just in Kotlin. So instead, probably what we'll do is just write the insertion, updates, and deletes directly in Swift instead of doing it in Kotlin in that case. And then finally, for the last one, we're going to ask if the query side is platform agnostic. And this is the really simple one. Queries is just a very simple API where you take a string and then return a list of search results, which are just a data class. And so this one is very platform agnostic. And this is really like the bulk of the logic, like creating the actual SQLite query and being able to return those results. So this was like, if we go back to like Ben's little graph, like this is by far the biggest part of our code base for search. And so we were able to accomplish that like mostly in common main just because the query function was there.
All right, so up until this point, we've been talking a lot about our code in terms of these three source sets. But there's an important other space that's available and has lots of functionality in it that you can use, especially, well, specifically when you're starting a new multi-platform library on a team that already has working applications, and that's your host application. Your host application has all kinds of functionality already. It can talk to and authenticate with your backend API, and it knows all the routes and host names, domain names, what environments you should be hitting in terms of your backend API. It can also do things like talk to your application state. So it can tell you who the current user is. In PlanGrid, it can tell you what the current construction project that the user is looking at. And so to help bootstrap our mobile shared library and to help get us started, we did a little bit of work to basically take advantage of that and defer some of the work of moving those things into our shared library. And we basically do that by creating library initialization and making that part of our library. Now, this isn't a particularly groundbreaking or complicated technique, but it's certainly worth knowing, especially if you have a working application already. And so the way that this works is in your common main, you create a public Kotlin interface. And it's public so that your host application can see it. And then what you do is you have your host application create a class that implements that interface. And then it'll just provide that implementation as an instance of that object during library initialization. And now your shared library will have an object that it can make calls to through a Kotlin interface to basically use the existing functionality that exists in your host app. And each of your platforms can implement that interface and have it behave the same way. And so at PlanGrid, we did this to get sort of the networking and API stuff out of the way to allow us to get started very quickly when we first started this project. And so the way that this works, well, first, so networking in general, especially on mobile, can be highly platform specific. And a great example of that is like background downloads. So if your app does background downloads, like PlanGrid does lots of downloads of large binary assets for those sheets that I showed you earlier, those APIs and capabilities are very different in iOS and Android. But also, networking comes with a whole host of little subproblems that aren't necessarily platform-specific, but may not be something that you're ready to tackle in your mobile shared library up front. So for example, those backend API hosts I was talking about earlier, you have to know what the domain names of those are, as well as know which environment your app is running in. And that's logic that you could start off by duplicating. You could start off by moving it in. But it's also not really necessarily the end goal of your library. It was not to handle talking to your backend API. So the other thing it can do that your application can do that you may not want to do yet is take your current user's credential, which is stored somewhere securely on your device, and turn that into something that you can authenticate with your backend API. So it's just important to know that there's a bunch of subproblems that come with basically interacting with your backend API. So at PlanGrid, we created a Kotlin interface, literally called network. And it's a pretty simple one. It just allows us to make an API request. And API is very specific there. It's not for general networking. It's just for making requests to our backend API. And then we can receive an asynchronous response from that. And the nice thing about this technique is that this doesn't prevent us from moving all of this into, sort of natively in Kotlin into our shared library later. Since everything now in our shared library is going to be talking to a Kotlin interface, later on we could, say, re-implement it using Ktor or something like that natively. So it's certainly a good option if you want to bootstrap your library. So in the PlanGrid app, the network interface looks exactly like this. It's just called make request for making an API request. And I'll walk through what's going on here. So the first thing you give it is the API host. This is just an enum. It's not like a string enum or an enum that has some data inside it. It's just a bare enum that has basically a list of the internal APIs that you can make requests to at PlanGrid. So here, again, this crosses off a whole bunch of subproblems that we don't need to deal with to get our library started. We don't have to deal with knowing, forming URLs that have some base domain. We also need to know like what environment you're in. Again, like prod, dev, test, staging, whatever environments you might have. Then you pass the request object, which has like the path portion of your URL, the JSON body, query parameters, basically all of your request details. And then finally, you pass a completion handler that you want to be called once the API response comes back. And this just gives you a sealed class that represents the different kinds of responses you can have. So like an error response or a JSON response. And then finally, the host application provides a network disposable. This is just an interface that has a cancel method so that the shared library can call cancel to cancel the request later on if it needs to. Now, this this way of doing networking with a completion handler isn't necessarily the best way to do asynchronous work in Kotlin. But it works really well for interop. So Objective-C and Swift know how to do lambdas. Kotlin obviously knows how to do lambdas. And we can even figure out how to make this work on Windows. But in Kotlin, inside of our library, we prefer to use coroutines, which don't necessarily interop well with platforms outside of Kotlin. So internally, we actually just wrap this into an internal-only suspend function that calls that original function and suspends until we get our completion back.
Yeah, speaking of suspending functions, concurrency is like a really major topic that you'll need to think about too once you start working in Kotlin native. It's much more complex than we could go over just here, so I'd highly recommend checking out like Kevin Galligan's work on this. He has a talk later at this conference, but also some blog posts on it that go into this in much more detail, which is really useful. I will say high level, the thing that I think is most important to get across is that if you're working in the common code base, you want everything to be immutable as much as possible. And not just immutable, but this concept of frozen. Essentially, when you're in the Kotlin native world, you can declare some memory as frozen. And when something's frozen, it's actually immutable on the memory level. So not only that object, but all of its references also get frozen. And then none of the values that are held within that block of memory can ever be changed. The way you do that is through a Kotlin native API called just freeze. You just call it on any object, and then it'll give it to you back, but in a frozen state. If you want to be able to use this from common main because you want to be sure that some code in common is getting frozen, you can just do this little trick. It's very simple, where you expect the freeze function to be there. In Kotlin native, you do call the actual Kotlin native freeze function, and then in the JVM, you just return the object without doing anything. But yeah, for more information on this, I'd highly recommend checking up other topics as well, because this can get pretty complicated. OK, so now we've given you the tools that you need to actually build a Kotlin native framework or a Kotlin multi-platform framework. So the next part of this is actually going to be shipping it. And there's two parts to shipping it. There's shipping it internally and externally. And so I want to talk about shipping internally first. And this is, to me, one of the most important things, I think, with multi-platform, which is essentially how are you organizing all of this code? Because with both Ben and I, the reality of it is we're working with these much larger teams, and we need to be able to work in a way that's actually effective. And so introducing this new common code introduces a ton of new problems just in how you work with other people, like the build tools, the CI, all those kind of things are going to get changed by introducing common code. So what are the different ways you can do that, and what are the pros and cons of each? The other thing to keep in mind is we've been talking about this as a host application. The reality is there's two. So these are kind of the code bases that we're working with: Android, iOS, and then the shared source sets. At least in Ben's case, there's also the Windows one, but you could have multiple different host applications here. So those are the things that you need to consider. The first option you can kind of take here is creating a monorepo. So if you look at the Kotlin multi-platform samples on GitHub that JetBrains has published, that's a good example of just a monorepo, where you have your source sets, and then the host applications all live side by side in a single repository. There's a lot of pros to this one. There's minimal change for Android. I mean, this is almost always going to be a benefit. But the idea that if you checked out the repo one day and it was now a monorepo with common code, as an Android developer, nothing will have changed. You're not compiling the iOS app, and it's still just a Kotlin tool chain. So that's really nice. Seamless local development is huge. When you actually have the common code next to the code that you're running, then you can step through it and be able to debug it really easily. As well as a single source of truth. You don't have to worry about which artifact are you pointing to, especially if you're going back, maybe bisecting or something like that. Do you need to worry about those artifacts still being around? It just lives in the repository, so you know where that source of truth is. And then perhaps the biggest one is host dependency. So that idea of being able to depend back to the host application or the rest of the module from common code. So if you do want to have some sort of expected actual, where the actual is coming from something you've already previously written, doing a monorepo is going to let you do that. The downsides to this is you're introducing a lot of new stuff to iOS. Having Gradle as a build environment for iOS can get really, really hairy in my experience. It's not even common for iOS developers necessarily to have the JVM working on their computer. So you now need to take into account that you're introducing the JVM for their entire iOS build toolchain. And so there are problems that can come up with that. There's problems that could come up with Gradle. So just executing a build now all of a sudden is a little bit more complicated for iOS developers. It's not necessarily that this is a very bad thing, but this is something you should be aware of that you will have to support. And especially in my case, where I was coming from the Android side, I had to make sure I was there to support the iOS side. CI is another story, especially on iOS. CI tends to be like pretty bespoke. So you're always going to be running these like Gradle tasks, at least like locally with iOS. If the artifact has already been built and then you go to do like an incremental build, it's not going to rerun Gradle. So for the most part, you're going to be fine. But on CI, it's always going to invoke Gradle. So you need to be able to have a CI system that's also going to be able to support both, which again, for Android is very straightforward. But now all of a sudden, if you're moving iOS there, you need to make sure that your CI is prepared to run both iOS as well as the whole Gradle toolchain. This isn't what we're doing on cache. What we actually have right now, because we were moving from 2 separate repos, the idea was we wanted to get towards a mono repo, but we wanted to do it incrementally. So the way that we accomplished this was essentially by copying and pasting common code. And so there's 2 multi-platform submodules. There's one inside of the Android code base and one inside of the iOS code base. And they both have the same copy of the common code. This has a lot of the pros, the same pros as the having the mono repo, although it's missing the single source of truth, which actually now becomes the biggest con, because those 2 code bases can get out of sync, and in my experience, like they are going to get out of sync. And the thing that sucks about this is like that was the whole point of doing multi-platform in the first place, was that you have a single source of truth for this business logic. So all of a sudden, if they start to diverge, that's a really big problem. In reality, like you just have to do the extra maintenance to make sure that they like get back together. But it is something now that you have to take into account. So this isn't really something I would recommend. It's more of like an incremental step on the way to something better.
All right, so in the PlanGrid app, we keep everything separate in different repos. So one repo for each host application, and then we spun up a new repo for our multi-platform shared library. And so there's some ups and downs to this as well. The first is that the first pro, in my opinion, is that CI is super fast, so we don't care about integration tests with our applications, no instrumentation tests or anything like that. You're just running the unit tests for this brand new library, which is already small, and so relatively few unit tests probably getting started, and so it's super fast, which is great. This is sort of a pro wrapped in a con, or maybe vice versa, if I understand that metaphor correctly. But basically, this setup does encourage really good unit test coverage, because when you have this setup, you have to be publishing builds internally. So you write some code, you merge it to your main branch, you publish it, and then you go to integrate it and sort of bump the version of your library on one of your host applications. Well, if you get to that point and you find that the stuff that you just wrote is crashing or otherwise not doing what you thought it did, now you have to go back and fix it and do it again. So this setup, therefore, makes you want to make sure that your code is very well covered and is doing exactly what you thought it did. And maybe this part goes without saying, but it's a single source of truth because there's no copying and pasting code everywhere. The biggest con to this is that breaking changes, and my team wished I could put this here twice, is that breaking changes are extremely painful. And I guess this doesn't really matter with any particular, like with this particular setup, but it's definitely felt with this one. So what happens is, let's say that I go make some public API, and then later on I change it. And then so as an iOS developer, I go and I update the iOS app, and then, I don't know, I get to updating the Android app tomorrow. And then one of my coworkers wakes up in Tel Aviv and sees that they now want to go include their change. So they upgrade the library past my version. And in attempting to integrate their new change, they run into my breaking API change and don't know what to do because they don't know why I broke it. I'm also asleep because they're in Tel Aviv. And now this is really painful for them. So to make this all work, as I've kind of talked about, you really need a good continuous delivery setup. So every time you're merging to your main branch, CI should be working on publishing a new internal version that you can go integrate in your downstream applications. The other downside to this approach is that because your repo is separated from all of the apps that it's integrating with, debugging and sort of getting a nice setup where you have your repo set up next to the live application you want to debug and getting everything connected to work correctly can be kind of challenging. And so Alec is going to talk a bit more about that.
Yeah, I think with all of these setups, the thing that should be pretty obvious is that you need to spend some amount of time getting the tooling set up ahead of time so that it's very easy to work with these repos in the future. One of the really great things you can do for both Android and iOS is with this shared repo, as long as you have it checked out on your computer, there are ways to actually swap out the artifact that's being distributed with the repo that you have on your computer. So when you're doing local development, instead of always doing against artifact and having to like redeploy it, instead what you can do is have the the directory that you have on your computer be the thing that's being compiled. With iOS, what you need to do is use CocoaPods and just have a separate pod file for development. And then it's pretty straightforward to have that pod file point to a local directory instead of pointing to an artifact that's been distributed. And then if you want to actually start developing in the common code base, you just swap out the pod file, and now you can start developing against code you have locally. The nice thing about this is it's opt-in, so now you're not forcing your entire iOS team to always be compiling with Gradle and with Kotlin. It's only when they actually want to go and start touching that code that they can use this trick. But as long as you have that pod file checked in, then it's actually a really straightforward process. You can do the same thing on Android using the include build tag. So in your settings.gradle file, you can actually add this block of code where you include build and then substitute a dependency with a project. If you Google for that, then you'll find the actual code block that you can use to do it. And then it accomplishes exactly the same thing. So now instead of downloading and using some artifact that's been deployed, you're just pointing towards some sort of local directory, and then you can do your development there. And now all of a sudden, a lot of those pros of a monorepo actually start coming back. You can do things like debugging in it really easily. And if you do need to do a long stretch of work in there, you don't have to worry about constantly deploying new artifacts to test it.
All right, so you made it this far, and you figured out your whole internal setup, and now you're ready to actually ship to the world. The most important thing that you should test here before you ship a version of your library with an application is actually test crashing, which sounds kind of weird to say out loud. And the reason is because, well, on the JVM side, again, you can lean on your expectations of what you had from working in just the pure JVM world. But when you're using Kotlin Native to build your repo for iOS, expectations are a little bit different. Symbolicated crash reports is sort of an improving area of Kotlin Native, especially 1.360 brought a lot of improvements there. So it's really important that you just write a function that crashes. So here we're force unwrapping a null, and call this from your ObjectiveC or Swift, and see what kind of crash trace you get, and make sure that that's something that, if you saw that in production and didn't have the code in front of you, you could kind of decipher what that meant. And in Kotlin Native, there's something to help you. It's called set unhandled exception hook. It's a Kotlin Native only API. And setting this hook, that hook will be called just before the application crashes with the throwable to allow you to log any information you might need to log there. The other thing that we ran into when testing is that basically, if you're using the worker API, and so if you're not familiar with what a worker is, this is a Kotlin Native only API that's essentially an abstraction around threads. So if you're using a worker to do background work and your background work crashes in a worker, the default behavior is actually that it crashes silently. So your application won't crash at all. The worker will just kind of stop. In the PlanGrid app, this is sort of not what we expected, and we would prefer that our application actually crashes. So we did some extra work to ensure that if an exception made it that high, it would actually crash the app. So definitely something you'll want to test if you're using workers.
Sweet. And that's really all you need to know from those 3 steps, educating your team, actually building the product, and then what it takes to really ship it. But there's one more thing I really want to talk about, which is that community involvement piece. Because I said that was one of the most important things that I think is a pro for Kotlin multiplatform. And if you're starting to use this, you should really start to contribute back at well and start to make that community something special. And to illustrate this, I'm going to share how Ben and I actually got to know each other. So around a year ago in the Kotlin Lang Slack, he had posted this snippet of him getting CocoaPods working with Kotlin Native. And at the time, that was when I was starting my integration too, and this was the initial hump that I needed to go through. So it's sweet, pretty much solved my entire problem, but I was like, this would be much better served in a Gradle plugin so that other people could be using it without having to copy and paste all the code everywhere and have that single source of truth. So we turned it into a Gradle plugin and deployed that. That ended up catching the eye of JetBrains, where they decided, OK, we need to have CocoaPods support actually built into Kotlin Native as well. And actually, there's a line there for the first problem, the same approach as in this third-party plugin. That's the one that we ended up writing together. And so a lot of that code ended up getting upstreamed and is now in Kotlin Native, where it's much better maintained, and there's a whole swath of new support and features for the CocoaPods integration. So it's this really nice thing where we didn't do all that much work to begin with, but we shared what we were working on, and we're able to work together to move the project forward in a direction that we thought was important. So definitely, if you get involved in this stuff, it's like Andre was mentioning in the keynote. You can be liking or retweeting stuff, or just upvoting U-tracks. All that kind of stuff is contributing back to the community. So I really encourage you to do that.
All right, so that's it for our talk today. I'm just going to go over sort of what we talked about. So again, it's really important to define your project's goals so that when you're getting set up, you understand why you got into this and what it means for your project to be successful. It's also important to be thoughtful about growing your code base. Don't let it become something where over time your platform-specific source sets get really big, and then you're back to where you started before you had this nice space where you could have common code. Avoid trying to solve general multi-platform problems. I use networking as an example, and there is KTOR out there. But if you find your networking stack has a lot of little subproblems associated with it, you feel free to just defer that to your application since it already knows how to do that, and you can just solve them later. Get your CI and dev setup working early. I think we've said this a few times. And finally, just join us in the Kotlin Slack, and thanks for coming.